And what we want to devise or want to figure out is actually small molecules that actually will stabilize this and shift this by mass action effects, shift this toward a folded form, right? So this is very simple. And in the absence of these correctors, this is the common aggregation, common event. So problem, of course, is rapid identification of potential therapeutics for folding, because these proteins are moving targets, right? So we use this chaperone as a capture system. So this chaperone actually captures proteins that are misfolded or partially folded. You have hydrophobic patches, and they actually capture them. So the nice thing about this is we got a nice readout if we have a corrector that actually prevents this from journeying into these misfolded forms. Then we populate this. We no longer partition onto this detector system, right? And we use surface plasmon resonance or biolayer interferometry to actually, it's very simple. Because I have a simple mind, I can't, simple-minded solution from a simple mind. All you have to do is realize that with these two particular instruments, you're looking at mass changes, right? So that's all that's all the technical stuff I'm going to get into as far as these. But this is surface plasmon resonance. What you're looking at here is that if the protein is destabilized, you're going to have the chaperone bind. And it's going to be a large signal because this has got a large mass. And if you have then you flow over a corrector, now you no longer see that interaction here, and you have a diminished signal. So that's where you can actually detect whether or not this is actually working. And with biolayer interferometry, it's the same deal, where you're looking at a decrease in signal. You have the chaperone that would bind to the protein that's partially unfolded here, and in the case of a corrector here where I have a C, that would actually diminish that. So how can we use this? Let's just one example and then I'll end. So here, for instance, Parkinson's disease. Parkinson's disease, a diagnosis, they called it Lewy bodies. These are synucleinopathies or aggregates, and you can actually see these aggregates in the brain, in brain slides and staining and so forth. Alpha-synuclein had an unknown function for a long time. It turns out that these are important for neural transmission of vesicles and so forth for your neural transmission. So they're also found in RBC and neurons, but there's also sporadic and genetic Parkinson's disease. So problem of this is dynamic equilibrium. We're trying to catch these pre-aggregates before they go into these large aggregates. The toxic states turn out to be not these disordered or large aggregates. They're these soluble forms. So they actually interfere. One of the targets that the Parkinson's actually binds to is actually the mitochondria. So it interferes with all that transport of all those proteins into the mitochondria. That's one of the reasons why you start to lose energy and so forth in it. So what we want to do, so you can get either a missense, a truncation, or a point mutation, and that actually you run into aggregation. And you have these unfolded monomers. So one way of doing this is actually to devise what we call pharmacological chaperones. So pharmacophones, pharmacological chaperones, these are small molecules that bind, also correctors, right? So cystic fibrosis is one of the drugs that are on Vertex, is actually a corrector of sorts. It actually corrects the misfold. So challenges in drug design of protein folding diseases, we have to validate these stabilizing effects. We have to look at binding affinity. Sometimes binding affinity doesn't result in stability. So we have this detection system that actually can detect whether or not the protein is actually stable. So what we do is actually use the chaperone as our detection system, right? So if this unfolded monomer is around, the chaperone will promiscuously bind. This is very promiscuous. I'm not kidding when I say promiscuous. These things are very sticky. They are bind to everything. It was a bear to actually purify this protein when I started in 1992 on this. And I was one of the, so they're using the extinction coefficient that I measured, because I got the purest stuff west of the Mississippi, or actually, what was it? I was actually in Bethesda at that time. Now I get the best stuff west of the Mississippi also. So we produce this stuff in high quantities and so forth, highly pure, and get rid of these. So alpha-synuclein, turns out, has a folded structure. This actually binds to membranes and interacts and fuses vesicles for nerve transmission. But the problem you have with the fold is, of course, you have to keep these in an alpha helices. And a collaborator of mine, Quinn Hung at IU, actually and a medicinal chemist, devised a compound that would actually stabilize alpha helices. And you can see alpha helices here. This was designed to actually stabilize these. So we want to determine whether or not this candidate actually stabilizes the protein. And so we want to correct the defects, we want to prevent the aggregation, and we have this, what this compound is called Q4. Great name, right? But that's one of the reasons they hide the names, because they don't want people copying the marketing. And so I don't care, really. I want these chemicals, these pharmacological chaperones out on the market and so forth. So anyway, correcting the source of misfolding. Just to compare, here's aggregation assay. If you were simply looking at aggregation, this is 140 hours. Right? You put this in a test tube, you have to wait 140 hours before this aggregates, right? This, we don't have any aggregation, but this is attached to the surface. But now we have Q4 that diminishes this in, let's see, we can actually tell within 150 seconds that this is working. So this is the way that we are approaching folding diseases, and we've done this with, we can look at ALS, superoxide dismutase mutants, cystic fibrosis. We've used Friedreich's ataxia for taxin. Von Willebrand disease, which turns out to be a bleeding disorder. That's 1% of the human population is affected by that. And that's a folding defect also. So the world is our oyster as far as this is concerned, and we've actually collaborated with a computational chemist at KU who's actually designing these small molecules to stabilize dynamics. Remember, proteins are moving and shaking and so forth. If you stabilize a site, the proteins are not just these static. You have to actually think about the dynamics, and they'll stabilize that dynamic fold. And we've actually been able to reverse misfolding of a cancer protein called P53. It's really important in breast cancer. And we watch in cells actually reversing the misfolding of P53 and regain function of the P53. And what that does is actually kills cancer cells. So we're on the right path, I think. So here's a targeted fashion. This is the one that's out for transthyretin. This thing breaks apart and aggregates, but this compound will actually bind and stabilize this and prevent neuropathies and then cardiomyopathies and neuropathies. And this is actually commercially available. So this is really truly a mode of now new medicines that are coming to bear, are coming to fruition, but we've actually now been able to provide these companies with a way to detect whether or not you get stability or not. So protein folding is are prevalent. 3 strategies to ameliorate or decrease. You boost the molecular chaperone levels. That's one way. Small molecule stabilizers, pharmacological chaperones, and a combination of both, which actually turns out to be the best way to do this. So at that, I can take any questions you may have, and hopefully this was informative for all of you. Any questions? Yes?
Could you explain to me a little bit about how the protein is folded when the ribosome makes it? Like, how much does the ribosome do? And are the chaperones that we're talking about, are they part of what makes them fold correctly?
Yes, they're actually, so as the protein folds, right, it's coming out in a string, right? And sometimes you'll have alpha helices that'll collapse and then disappear and collapse and disappear. These are very dynamic, right? And the chaperones, there's a lot of chaperones that actually sit on the exterior of ribosomes and facilitate folding, catch them before. They don't facilitate folding as much as they prevent. They're what chaperones are, right? Chaperones prevent inappropriate interactions, right? So that's what chaperones are. They prevent inappropriate interactions. So that's what they're doing. They're preventing these hydrophobic collapses to occur prematurely as you're producing this protein, and will stabilize these proteins. And these heat shock proteins are absolutely essential. The one I've talked about here, the chaperonin or the GRO-EL, that if you diminish the amounts of that, how this was discovered was in mitochondria. There was infants that were dying prematurely. And it didn't look like there's anything wrong with it. Turns out they had lower levels of chaperones in their mitochondria to help proteins fold. Once they get transported in, they unfold and they refold on the other side in the mitochondria. It's the same way as they come out of the ribosome. They're kind of cute, almost like toothpaste, right? But this toothpaste has very specific interaction sites. So, as the amino acids and the string of polypeptide comes out, they actually fold up on themselves in a three-dimensional structure that resembles, that is functional. So to answer your question, this is a long answer to your question, but yes, there are chaperones that are on the outside waiting, nursing the protein, preventing inappropriate interactions. Some proteins really fold fast and they don't need chaperones. So, yes?
So you said the word that I was hoping you were going to say is fast. My question is about timescales.
Right.
So you talk about proteins folding. You also talked about Alzheimer's and how it's a disease typically of the aged. So you're talking about diseases which take a long time to develop and show up. You're also talking about events which take place on picosecond or nanosecond timescales. How do you deal with those two timescales which are completely
So you paid attention to that second slide, third slide? So aging, guess what declines when we age?